Welcome to the Water Resources Podcast. I'm your host, Bridget Scanlon, from the Bureau of Economic Geology at the University of Texas at Austin. This podcast is produced in partnership with the National Academy of Engineering. In this podcast, we discuss water challenges with leading experts.
Claudia is the Program Chief for the Groundwater Availability and Use section at the U.S. Geological Survey in California at the Water Science Center in San Diego. Thank you so much, Claudia, for joining me today.
Thank you. It's nice to talk to you.
Claudia and I have known each other for decades, and when we chatted the other day, we caught up on all her dressage riding, and she's a very accomplished equestrian and will be competing at very high levels this fall. So I wish her the best on that. But we won't be talking about that today, unfortunately. We'd like to talk about the recent paper that Claudia published in the journal Groundwater, and the title of the paper is called Sustainability and Land Subsidence in California's Central Valley. So Claudia, maybe you can describe a little bit about the findings from that study and if there were any surprises or, how it evolved.
Sure. So what we did is we looked at the Central Valley groundwater availability in relation to the Sustainable Groundwater Management Act and really focused on subsidence. And it's basically, we updated the Central Valley Hydrologic Model that was released more than a decade ago to analyze some of the regional information and look at subsidence and water availability issues. Much of the results are the same. There's been continued losses in storage, particularly during like the 2007 to 2009 drought and 2012 to 2016 droughts. And so a lot of the groundwater availability changes are a result of climate variability, land use changes, and some of the restrictions on surface water flows. And all of this has kind of resulted in significant amounts of land subsidence that has affected a lot of the infrastructure, mainly the canals that transect the valley to deliver surface water.
Right. And so you mentioned the Sustainable Groundwater Management Act, and I think that was passed in 2014. Right. So maybe you can describe how that came about and why it was successful, the passing of that. It's pretty difficult to pass some of these things. So I know it's the middle of a big drought, 2012 to 16, so that helped.
Right. Yeah, this is kind of the first real groundwater legislation, and like you said, it was passed in the middle of a drought, which I think had some impact in passing it. It required about 127 of the high and medium priority basins form groundwater sustainability agencies and to develop groundwater sustainability plans. I think one of the other things that really helped to pass it and what makes it important is it looks at things from the locals' perspective, and the locals control and manage the system, and then the state comes back in as a backstop if they aren't able to manage the water. The state, they've had about 5 years or so to develop groundwater sustainability plans. All the plans have been developed, and the state's reviewing them, and then the state continues to review them every 5 years, and they update them and point out concerns.
So it's a bottom-up approach then, with all of the groundwater sustainability agencies developing plans, and then people reviewing those plans. And if the agency cannot manage it, then the state can come in and take over. And I think, it was the middle of an extreme drought that extended from 2012 through 2016. But also, I think, we have more remote sensing data these days, and that provides a visual of what's happening. And I think the gray satellite data provided a really nice picture of the evolving drought and the increasing groundwater depletion in the Central Valley over that time. And the INSAR satellite data showing subsidence and stuff. So these remote sensing products, I think, help communicate the issue to the public and to legislators and stuff. What do you think? How important do you think that was?
Yeah, I think Grace and INSAR provided a lot of good graphics, and we're able to show information visually to show the storage losses and to put kind of concrete numbers and maps of the storage loss and the subsidence. I mean, Sigma has, 6 main different parts to look at sustainability: the groundwater level declines, storage losses, seawater intrusion, water quality degradation, and then the interconnectedness of surface water depletions, and then the land subsidence. A lot of these things are below the ground and hard to see, but you can, with the INSAR data, you were able to see the lowering of the ground surface and the actual changes in the ground surface, so it makes it more visual for people. And then also the GRACE data actually shows a lot of the storage losses on a big, large map, so that you can see based on gravity the amount of storage depletion that has occurred throughout the world.
I recall many years ago, Claudia, that you were in a 60 Minutes program with Leslie Stahl. And, what I liked about that 60-minute episode was that they gave equal weight to the remote sensing and the GRACE satellites, and then to the ground-based monitoring and what the US Geological Survey has been doing for decades. So it was a really nice overview. I thought they did a great job of representing the issues and in a balanced way.
Yeah, I think they did a really good job too. It was like my 5 minutes of fame.
Well, at least you had 5 minutes. I'm still waiting for mine. So the Central Valley model, Central Valley Hydrologic Model, CVHM, you mentioned that you had published a previous report, USGS report in 2009, which was the Bible for the Central Valley. I mean, everybody went to your report and you had it all together. And what I really liked about it was everything was together. You had all the parts of the water accounting, and then you had the storage losses and the subsidence and everything. And so this recent paper also is fantastic. You modeled the system from 1962 through 2019 over the entire Central Valley. So that gives a really nice long context. I mean, GRACE satellite data are very nice, but we've only had them for a couple of decades, since 2002. So really trying to understand how the system has evolved over many decades, I think is really important. Another aspect of your recent paper that I absolutely loved was, you said you use ModFlow, one water hydrologic flow model. And I think this one water concept is really nice, because you integrate surface water and groundwater, and then you link land use and irrigation and water demands, and then subsidence. So bringing it all together, you can see the feedbacks between different things. So maybe, the USGS is well known for all of its work over the past century on the Central Valley. Maybe you can let people know what the Central Valley is like, how deep it is, the geology, and how the system has evolved over the past, since the early pre-development period.
Sure. The Central Valley is a big, large structural trough that's filled with sands and gravels and silts and clays that have been shed from the surrounding mountainsides, and they kind of fill up the valley. And we think of it as one big kind of sandbox, but it's really only about 30% sands and gravels. It's got a lot of clays that kind of confine or semi-confine the system and kind of pressurize it. There's a large and extensive clay body called the Corcoran clay that really confines a lot of the system in the south. And the deposits are kind of coarser to the east and southeast, and that come from large alluvial fans off the Sierra Nevada mountains. These coarser deposits are excellent sources to recharge the aquifer system and play an important part in how the water gets into the ground. I like the fact that you brought up the one water hydrologic model. We do need to think of it as one big integrated system. And California and the Central Valley in particular uses the water conjunctively, it's called. So we use both surface water and groundwater to meet our demands. And even the snowpack is one of the kind of reservoirs that we use to get at the water. So a lot of the snow falls in the winter up in the mountains. And then as that melts, it goes into the surface water system. And there's a series of reservoirs that are operated to control the flows down in the Central Valley. And these are, have multi-purposes for flood control as well as electrical generation, and to distribute the water to different parts of the valley for irrigated agriculture. It was a large alluvial valley that had lots of water. When the first wells were drilled in the southern part of Central Valley, or flowing wells, big tule marshes, and that slowly changed with irrigated agriculture and the pumping of groundwater to meet demands when there wasn't enough surface water available. So the large marsh areas were drained, and the valley is now mostly covered. It's a very flat valley. It's mostly covered with agriculture. There's still quite a bit of native vegetation in places as well. But as they pumped more and more of the water, there started to be subsidence and not enough water on the western side. So the state and the federal government came in and put in the Central Valley Project and the State Water Project to redistribute and move surface water around to get it to the areas that had some of the subsidence and extensively lowered groundwater levels. Water levels in some of these wells were lowered hundreds of feet because they come from a very pressurized system on the west side. So the surface water and groundwater has been moved around, and it's engineered to get water where we need it. But as agriculture has developed, and then they got those water projects in, subsidence was pretty much arrested and stopped for several decades. And in the recent droughts in 2007 to 9, subsidence reoccurred. But some of the subsidence locations are different than they were historically. They're now in different spots that don't have as much access to surface water in some areas, and some of them are resulting from some of the demand hardening from the crop changes that have taken place. In the last couple decades, there's been a strong increase in trees and vineyards and things like almonds, pistachios that take water and are a lot harder to fallow. What used to happen a lot of times in the Central Valley, and still does in some areas, because there still is extensive truck crops, but at least the truck crops and annual type crops you could just fallow and not grow for a year. But the trees need water, and they're a big initial expense for the farmers to get them up and producing, and takes numbers of years. So you can't just not water them for the year. So there's this thing called demand hardening to meet the demands for those trees. So that's had a large effect on the amount of water and timing of the water withdrawals needed for the irrigated agriculture.
So yeah, so it's really amazing how the system has evolved over time. I mean, you mentioned it's a big graben, 5 kilometers deep in the southern part of the Central Valley and 10 kilometers in the Sacramento area to the north. So this is extremely deep alluvial system, but 70% is fine-grained. And sometimes people say, how much it's important for us to know how much water is in the system. And to me, that's almost irrelevant, because you're never going to pump from that great depth, and you'd subside it to death before you would, and the economics of it. So there's other factors that would limit how much water you would produce besides how much is there. So very thick, very deep system. And then, it was originally a marshland, and you had to drain it to grow crops and stuff. And then, when it was artesian water, when the water was coming out of the wells under artesian pressure, people thought it would last forever, the psychology of it. And we had similar things in Texas, near Dallas, Fort Worth, artesian wells, you thought it would never stop.
Right.
And then, of course, overexploited it and a lot of depletion. But then you engineer the system a lot. And so, the journal article, California's Pipe Dream, where you created the Central Valley Project and the State Water Project, those reservoirs and canal systems to move water from the humid region in the north near Sacramento to the semi-arid regions in the Central Valley. So, nowadays, I don't think we would build something like that because it's so expensive. But we did in the 50s, 60s, and became effective then in the 70s and 80s, bringing water from, and then that stopped the depletion of the subsidence for a few decades. Right. But then, you said the change in crops, the economics of nut trees and all of that sort of thing, Sometimes people, many years ago, I was big on touting vegetarianism, and then, I began to realize, well, it takes a gallon to grow an almond in California. I'm not holier than thou, Maybe it's important where we grow these things, not just how much water they use. So it's really continually evolving. But what's nice about it is that you conjunctively use surface water and groundwater, these irrigation districts. And that to me is unusual because many places, they use either surface water or groundwater. Very few people keep the infrastructure going to maintain both. And I know I visited Arvin Edison many years ago, and it takes a lot. They price the water so that they keep both systems active and all of that sort of thing. So, but that helps. So during a wet year, you have a lot of interannual variability, floods and droughts. So during wet years, then they can use the surface water, and the surface water deliveries are high.
Yep.
And now they're using managed aquifer recharge. And then during dry years, then the groundwater provides the backup. So it's quite an interesting system. And then you're modeling, you integrate all of these data and you account for all these. That's just such a career to get the delivery data, to get the use data, to come up with the geology and everything. Maybe you can describe a little bit about developing the model and the geology and all of the detail that goes into it. I think it's like a square mile grid, and so it takes a lot to get the data together.
Yeah, the model covers about 20,000 square miles that cover the Central Valley, from Sacramento Valley down south to Bakersfield. It has 13 layers in it. The first 5 layers are above the Corcoran clay, the big confining layer, to look at some of the details in the kind of the upper parts of the system. And then 3 layers in the clay to really get at the changes in groundwater levels and heads across that pretty tight clay. It's not clay, solid clay everywhere, but it's a pretty good confining layer. And then 5 layers below it. The model runs from for water years 1962 through 2019. A water year starts in October of the previous year. So it has monthly stress periods. So we gather the data for the surface water deliveries on a monthly basis. It has land use maps mapped out, what's the dominant crop every 1 square mile, and those change through time. They change on a monthly basis as well. And then the streams are simulated as the inflows as the reservoir releases, and then as the streams goes down, it can gain or lose water from the groundwater system. And there's diversions off those streams to deliver it to the different water accounting units. And that's the whole area is originally split into 21 water accounting units. We've updated that a lot. There's 135 now. A lot of those more detailed delivery units where we have the accounting are along the Delta Mendota Canal, because a lot of effort was put in to look at subsidence along the Delta Mendota Canal. But some of those accounting units are where the different managed aquifer recharge water banks are, so that we can really add into this model the water banking and how much water is added through managed aquifer recharge. So there's a variety of things. It's the land use that drives the the water budgets and the demand, because in most of the valley historically, pumping has not been metered, so we really do not know how much water has come out through time. We're backing that out based on the land use and irrigation efficiencies and these water level changes to get at the amount of groundwater pumping, and that's calculated by backing it out on a monthly basis. One of the neat things about Sigma is all the data that's now available and being kept track of. We now are starting to get some data on pumping at the GSAs, but also really getting at water levels, and some of the companion legislations with Sigma have required monitoring of the different groundwater levels, and that be provided to the public. So one of the big wins for Sigma, even if it's having a hard time because of the recent droughts, of reaching sustainability, though we still have many years, according to Sigma, to I think till 2040 to get at sustainability, is that all these data are available. So now we can start to understand the system and really have a better knowledge as to what's going on.
And that's fantastic. I mean, it's, you know, all of the data that are available online, the groundwater level data, as you say, and the reporting and the transparency, the satellite data, the INSAR data, the groundwater monitoring data, and the groundwater levels. It's fantastic. I mean, that's probably a huge difference between when you did the original Central Valley Hydrologic Model that was published in 2009 and this recent effort. But that just means it's just 10 times more work than to compile all that data, but you have a lot more information to compare your model to and to calibrate the model. And so I think from over the period that you simulated, then you estimated maybe, was it 158 cubic kilometers of depletion, groundwater storage depletion over that entire period from 62 to 2019. Is that correct?
I think so, something of that magnitude.
Right. And a cubic kilometer is similar to 1.2 cubic kilometers is a 1 million acre feet for people who are more familiar with those units. So that's a lot of storage space that you have created, and there was more created prior to 62. And so, you know, that creates a big reservoir that we can store water underground. You know, traditionally we think of just storing in surface reservoirs, but we have huge space underground. And then your geology is very favorable for managed aquifer recharge. You have coarse sediments, you know, the spreading basins, the water can infiltrate, you know, fairly rapidly. And, you know, so that's really good, I think, you know. And we need to take advantage of that more and more in the future. Maybe you can describe some of those managed aquifer recharge programs and the different approaches that they use to store water.
Sure. So the managed aquifer recharge, there's different ways for doing that. You can either inject water through a well or put spreading ponds. One of the more popular things that they've been doing lately is doing what's called flood mar, where when we have these big extreme storms from atmospheric rivers and stuff, there's a lot of water and extra water at the time. And so there's flood flows, and they can divert those flows onto some of the agricultural lands that are acceptable for that. Not all of them are. And spread the water on the ground so it can seep into the ground. One of the problems is, you know, surface water can move very fast and very flashy, but the ground can only accept water so fast, and it's dependent on the permeability of the materials. So we have to, in order to really capture and utilize more of these storms and extreme events, we need to build some infrastructure to pond up the water and let it seep into the ground at the rates it can accept it, or move it around to different areas that are more gravelly or sandy or coarser, so the water is more likely and can seep in more fast at a faster rate.
Right, and I think another approach that you mentioned in your paper is in lieu recharge. So where the people that were normally using groundwater would switch to surface water, and then they would get credits for that, right?
Correct. A lot of that's being done in the southern Central Valley and has been being done for several decades, where they'll manage the water conjunctively in a lot more detail so that they can use areas that used to use groundwater can use surface water instead.
Right, and these irrigation districts like Arvin, Edison, Kern Waterbank, Fresno and stuff, they've been doing these managed aquifer recharge since Arvin since the 60s.
Right.
And I mean,
It's been going on a long time, but it's been increasing a lot rapidly in the recent past.
And I think
a lot of these, I'm sorry.
No, go ahead.
A lot of the groundwater sustainability plans really depend on managed aquifer recharge to help balance the budget for the ins and the outs, and they're really, counting on getting a lot of this water into the ground and managed aquifer recharge. So how that develops is going to be very interesting to make sure there's not some double and triple accounting of some of this water.
Right, right. So somebody upstream might take the water, whereas somebody downstream might be thinking they're going to get it, and so that will have to be managed carefully and coordinated. But you mentioned an important thing also, you have long-term droughts at different times, but then at the end of those droughts, oftentimes you have atmospheric rivers. And I think you saw that in, I mean, it's like Mike Dettinger had a paper titled, Atmospheric Rivers Drought Busters. And it seems like you almost need an atmospheric river to bust those droughts that have extended. So in 2017, after the drought from 2012 to 2016, there was a family of atmospheric rivers and a very intensive, and then you get so much water that you can hardly manage it. And similarly, last year, 23, ended a previous drought that had lasted for a few years. So the big challenge then is managing these extremes, and as you say, the infrastructure, and you need some sort of interim storage because you can't get it into the ground fast enough. I was really fascinated looking at Arvin Edison and their accounting and everything. I mean, during a drought, they're just taking water out. They have all their pumps going 24/7, 365, and then if it's a multi-year drought, then it's difficult. But then during the wet years, then they're putting that water into the aquifers. And I think, another thing that your model showed was during the very wet years, there's a lot of surface water recharging groundwater and flood water recharging aquifers also. So that's really nice to see. So this exchange between surface water and groundwater is very helpful in trying to manage the resource.
Yep.
So you've done a lot of work on subsidence. We've all seen that classic photo of Joe Poland, with the electric pole and the 9 meters of subsidence from 1925 through 1977. I guess that's southwest of Mendota. And then I saw some images online more recently near El Nido from 65 to 2016, about 2.5 meters of subsidence. And so that's really impacting these canal systems, then these conveyance systems. And so that may put a limit to water use, I think, before, groundwater level declines. So that has advanced a lot, and your new model, you deal with different types of subsidence, instantaneous and residual subsidence. Maybe you can describe that a little bit, and the amount of compaction of these clays that results in the subsidence.
Sure. So one of the big nice things about Sigma is they have different sustainability indicators, and one of them is subsidence. And in some areas, subsidence may be the key management criteria that they're going to have to mainly work with. The way the Central Valley has all these sands and clays interspersed, there's thin layers of clays and thicker layers of clays. And the thin layers of clays, as you pump the water out, they can drain relatively rapidly. The thicker the clay gets, the slower it drains. So as you start getting very, very thick clays, they'll take many weeks to months to years to decades to actually drain out. And so there's some estimates that the Corcoran clay may drain from the pressure reduction from all this pumping for thousands of years, not just tens of hundreds. So there's a look at this delayed and instantaneous response of these clays to how the storage is, the water is pulled out of storage from the clays. And as the clay particles are at, kind of random orders when they're laid down in the valley, as you pump this water out, those particles kind of compact and stack up more neatly, so they take up less space. And as they take up less space, you have a permanent loss of storage. You can't like unrearrange those particles at odd angles again, because they're in a lower state of entropy and they're down where they can stay compacted. So there's been this permanent loss of storage, and that permanent loss of storage is about 15% of the amount of storage loss is coming from the permanent loss of storage from compaction. There's some elastic that goes up and down in a seasonal year. One of the neat things of the different types of data that we have now is continuous GPS data, and you can really look at the GPS data, and the model is now calibrated to a lot of this GPS data, as well as INSAR, and these extensometers that you talked about for measuring the amount of compaction in different parts of the system. So we can see the response, and it goes up and down seasonally at a very small amount, but overall, still the change in storage and loss is a stronger downward from that more permanent loss of storage, and also from just the extraction from and drainage from the deposits themselves. That's termed like a specific yield.
So, I mean, you see regional subsidence, and then you see hotspots of subsidence in local areas. And then with the INSAR data, you became aware of new subsidence that you weren't anticipating. You thought subsidence was a done deal. You have surface water deliveries, you're done and dusted, that's it. But then, you saw the reappearance of subsidence with, maybe the crops, the nut trees and everything demanding more water and more groundwater pumpage, because they can't fallow and things like that. And then during atmospheric rivers, then you've seen the reappearance of the Tulare Lake, and maybe some of that is related to sort of regional subsidence in that area. Do you think that's linked to that, or subsidence there linked to?
I think some of the Tulare Lake and the flooding is from the extreme atmospheric rivers and the really wet years. The location of where the lakes formed and where it flooded, I think, has changed somewhat based on some of the pumping and the subsidence. The subsidence has caused the area around Corcoran to go way down, and they were really having to increase their levees to keep the lake from flooding the town and some of the infrastructure in that area. So that definitely has changed the flooding patterns and the land surface throughout the valley.
So I guess, a lot of extremes, drought, floods, and I was reading some papers recently that, they were saying between 2012 and 2022, about 4,000 wells went dry in California. And it's great that you have those data. I don't think we have anything similar in Texas, and maybe 3,000 wells going dry in the San Joaquin Valley. And I think with the Sustainable Groundwater Management Act, there's minimum threshold of depletion from 2019 through 2040. In some areas, maybe 30 meters that they would allow. And so some studies, Pacific Institute or others, are suggesting that, even community water systems and other systems, a lot of them could go dry if that amount of depletion occurs over the next couple of decades.
Yeah, it's something they're going to have to struggle with to figure it out. Each of the basins can get at sustainability differently, and they can change where they're pumping, or, maybe deal with it's the shallower wells that are going dry first, and the deeper wells are often the irrigation wells, or the irrigation wells from some of these larger corporations that have the finances to drill deeper. So how do you balance those different things and get at sustainability, and maybe where you locate your wells, and moving the surface water around, and even the groundwater to the different areas if these wells are going dry, or do you drill new wells? You have to look at all those different factors.
Right. And, you know, you mentioned that we have a lot more data these days to understand the dynamics of the system. And another aspect is the airborne electromagnetic data that Stanford Rosemary Knight has been critically involved with. And that's another source of data helping us understand the subsurface geology and these paleo channels. You know, you mentioned the alluvial fans coming off the Sierras, but underneath there can also be paleo channels. And so if you could understand that better and the linkages, then maybe you could target the managed aquifer recharge then to reduce subsidence in some of these hotspots as we get better knowledge about it.
Yeah, they're using a lot of the AEM data to try to look at these channels and where they can get water into the ground, and also where they might be able to pump so that when they get the water in the ground there, they can utilize it. And kind of combine those types of things so that you're pumping from where you're getting your recharge and not pumping where you're causing subsidence. So knowing the system and having these data sets really helps you be able to better manage the system.
And you know, with Sustainable Groundwater Management Act, then they're supposed to move towards more sustainable practices by 2040. So, I mean, I usually think of sustainability, you know, you can reduce the demand or increase the supplies or store or transport. And it seems like the Central Valley, you're doing everything, you know. I mean, you're maybe not so much reducing the demand because you have the nut trees and the fruit trees and the vineyards and everything. But the economics, I think, is driving that. But the supplies and storing, particularly, I think, managed aquifer recharge, and also people, the Army Corps of Engineers is looking at forecast-informed reservoir operations. So if they knew that there were no more atmospheric rivers coming, they could hold on to that water in the reservoir or send it downstream in Orange County for managed aquifer recharge. So it's amazing how creative we can become when, you know, the pressure is on. And so it's very interesting, isn't it, to see all of the different approaches towards sustainability.
Yep. It's amazing how the different agencies are all coming at this differently depending on where they are and what resources they have and what their geology looks like.
Right. I mean, and so you're facing a lot of challenges. I mean, you know, the snow cover, at least, I mean, I feel, you know, in California, if you don't have snow, you know, you don't have water to irrigate in the summer. But if you have these perennial crops anyway, you know, you're not going to follow them. Whereas in Texas, we get a lot of convective summer storms. So you plant and then you don't get the rain. So, you know, you don't have that advanced forecasting. So the snow is changing and the seasonal melting is changing, and that third reservoir, you know, all of that timing. So really what you're trying to do is manage the spatial and temporal disconnects between supply and demand. So you're having to modify a lot to adapt to these changes.
Yeah, they've always been able to manage things with the conjunctive use of water and moving the surface water and groundwater around, both, like you said, spatially and temporally. You know, it's getting tighter and tighter, and the extremes are getting more and more extreme, it seems, from looking at the climate variability in recent years. But it's amazing what they're able to do. And, you know, groundwater is kind of this buffer that when there's not the surface water available, during the droughts, they really heavily rely on the groundwater parts of the system.
Right, and you use the term, I think in some of your writing, groundwater banking, you know, I mean, you put it in when you can, when you've got the excess, and then you pull it out then during these droughts, and the longer the drought is, the more difficult it is. But I think, you know, the Central Valley Hydrologic Model is a great tool then for people to understand and to test different scenarios at a regional scale and to evaluate the impacts of different things. I mean, one of the things I was thinking, you know, when you have a wet year and you have a lot of recharge from, you know, rivers recharging groundwater, you know, if you thought, well, that's your managed aquifer recharge system, then you know you would be off base, and so having this model that integrates all of those different things, I think is a very useful tool.
Yep, I agree. It's a nice tool, and it's a tool to look at things on a regional basis. The GSAs, the groundwater sustainability agencies for each of these basins, and sometimes there's multiple GSAs for a basin, are going to need to develop more local tools to look at their local areas, and they are in most cases developing local models. But at least this provides a background of data and a way to like integrate and look at it on a more regional basis. And one of the, I think the good parts of both the CVHM that are the model we used at the USGS and also C2VSIM, the state's modeling efforts, is all the data sets behind them and them being available, and they can be used in more detail. And sometimes think of a model as something capable of being accurate everywhere, but usually they're tools and they're not perfectly accurate everywhere, but they have all these data sets behind them that people can use to build and understand the system.
Right, and you know, by integrating all of those different components, then you can look at the linkages and the feedbacks between them. So within the context of climate extremes and land use, long-term land use changes you mentioned. I mean, California, $50 billion agricultural industry in 2019. That's huge. You know, I mean, it may be something we shouldn't be touting that, you know, we produce a lot of our vegetables in California. It's a desert, you know, yep. After all, but that is the case. So one of the things that I thought was interesting about the model also is that, you know, you pump so much water, but only about 20% of it is coming from storage in the aquifer, and the rest is from recharge processes and stuff. And so I think that's something that people may not be fully aware of. And Lenny Conacow pointed out the same sort of thing at a much larger scale for the US on average. You know, the storage loss from the aquifer is only about, on average, 15%, he said, of the pumpage. So even though you pump a lot of water, then you capture recharge in different ways. So I don't think we're oftentimes aware of that difference.
Right, you're pulling water out of the ground, but water at the same time, water is seeping into the ground from either excess irrigation water or streams leaking or the precipitation falling on the ground. So you know, it's one, that's back to the one water hydrologic model. It's one big system that's integrated and the pieces and parts moved around, and there's a lot of reuse of water too, with the surface water being used several times, sometimes as it's used for one field and then downstream again on the next field.
Right. I mean, a lot of people say, you know, sometimes they say they don't want to reuse water, but they're not aware that, you know, the surface water from Dallas is reused about 10 times by the time it gets downstream. So whether we like it or not. So I know it's a huge effort to put this model together, and it's a great relief to have it out the door and everything. And I really commend the USGS in all of the data releases that they put out with all of their work these days. I mean, that's a huge and it's a great resource for us trying to figure out what's going on in different regions. So I really appreciate, I know it's a pound of flesh on your part, but it's really nice that you put all the data out there, and so it's readily accessible. So thinking about going through that entire exercise and stuff and working it for so long, are you optimistic, you know, about the future with Sigma and the situation in the Central Valley, or what are your thoughts?
I think I'm optimistic in some ways. I mean, I think, you know, things will have to change some in order to manage the aquifers and the water better. But we now have data and tools available that we didn't used to have. So I think the water managers have a more, you know, tools in their bucket to get at solving the problems. And Sigma's gone a long way to do that, to get a lot of the data available and public. I think people are thinking about it now, and starting to really realize, okay, we have to balance these ins and outs, and maybe, you know, we overuse the system in the drier years, but then we can recharge it more in the wetter years, and work with the variability in the climate. There will need to be some changes in order to get to sustainability, but I think once you know what the problem is, you can figure out how to solve it. Where before, I think we were kind of blind to that there was even an issue. And so I think that we're getting there, and we're starting to think about things and how to build infrastructure to get like the excess water when we have it into the ground, so that we can use it for a rainy day. So it's, you know, different type of mentality, and I think that that mentality is helping change and get at thinking about being sustainable. So I have a lot of hope for the future.
Well, I think, you know, your recent model really reflects all of the new data, and I think it's fantastic. I mean, I go on the web and I can see the changes in water levels in the Central Valley, you know, during a drought period, whatever. It's just amazing. And so having that data then helps communicate the issues to the stakeholders and helps them understand the remote sensing, ground-based monitoring, and the modeling tools. So I think that will go a long way. And, you know, I was so impressed when I visited Arvin and Edison and see how they were managing the water when I visited there many years ago, how they priced the water, you know, to keep the surface water systems going, and then give it to the higher value users early if it's a drought, or, you know, all of these different things. It's just really incredible. And I think it's kind of gives us an idea of what the future will look like, you know, as we manage the system in more detail. So yeah, I really appreciate your time. I know you're very busy, and I'm envious of your beautiful home, and I wish you best in your dressage this fall, and I wish that must be so exhilarating. Claudia's horse is called Quo Vadis, right? Q, I think is how you. So I wish you the best in that, Claudia, and thank you so much for taking the time to explain your recent work.
So yeah, it was great to talk with you.
Thanks.
Thanks.